Okay, so we're going to take a look at problem 2-73, and this is a force directed along a line. And here's the picture in the book. I drew my own in my solution, but obviously that's not the same quality. So give you a little shot there, and then we're going to go figure out how to solve this. So first what we have to do is we have to find the positions of the 3 points A, B, and C, because the man pulls on the rope at C with a force of 70 pounds, and it's going to cause force A and force C to be equal to each other in magnitude. And so we have to figure out those two forces, and we're going to find a resultant force, and then we're going to use that resultant force and the components of the resultant force to find the coordinate direction angles at B. So first what we're going to do is we're going to find the position of A, B, and C. And from looking at this picture right now, you can see that A is at 5, -7, 5. B is at -1, -5, and 8. And C is at 5, 7, and 4. And so on my sheet over here, you can see I've got those written down. And so the second step in this problem is we're going to want to find BA and BC, because going back to the picture, we can see those two lines are where the two forces are directed along. So in order to find a line, you're going to take the second coordinates and subtract the first coordinates from them. Make sure you have your orders correct, because if you don't, you're going to end up with a backwards vector. So after we do that, going over to my work, for BA, for the x component, it's going to be 5 minus a -1. It's going to turn into be a 6. So you guys don't get ahead of us here. I'll put this in front. For the J, it's going to be -7 minus a -5. That'll turn out to be a -2. And then it'll be 5 minus 8 in K for a -3. Now let's find BC. So it'll be 5 minus a -1 for 6. It'll be 7 minus a -5 to make 12 in the J, and then it'll be 4 minus 8 to make -4 in the K. So we have our BA and we have our BC lines, so what do we do from here? Well, in order to figure out how those forces line up along that line, we have to get them into Cartesian components, and the only way to do that is we have to find the unit vector that those forces are directed along, and then we multiply the magnitude of those forces by the unit vector. And in order to find a unit vector, we first have to have the vector itself, and then we have to figure out the magnitude, which is the square root of the sum of the three components. So going back to our vectors over here, to find the magnitude of BA, we're going to do the square root of 6 squared plus -2 squared plus -3 squared. It's going to be the square root of 49, so BA is 7 feet long. For BC, same exact thing almost. It's going to be the square root of 6 squared plus 12 squared plus -4 squared. After all the simplification, we're going to get that BC is 14 feet long. Alright, so we figured out the length of BA, we figured out the length of BC. So now we can work on finding those unit vectors, which, like I said earlier, is just as simple as dividing the actual vector by the magnitude, which you can see in step 3 right here. That is just simply our unit vectors for BA and BC. The vector divided by the magnitude. So from where we go here, we found our unit vectors. So now what we want to do is we're going to want to find the Cartesian components of the forces directed along FA and FC. So in the problem, it says the man at C pulls with a force of 70 pounds. Well, 70 pounds at C means that FC is going to be 70 pounds. And then it also says FC and FA are equal, so therefore FA is also 70 pounds. So in order to find the force vectors here, we're just going to multiply 70 by our unit vectors, which, go back to the notes here. So your force along BA in Cartesian components, you're just going to do 70 times your unit vector of BA, and you're going to end up with 60I minus 20J minus 30K pounds. Do the same exact thing for FC, and you're going to end up with 30I plus 60J minus 20K pounds. And so we found our force vectors of FA and FC in our Cartesian components. So now what we can do is we can add those to get a resultant force, and that is just as simple as adding the I, J, and K components together. So going over to step 5 in my work, we're going to end up with a vector of 90I plus 40J minus 50K pounds. Alright, so we found our resultant vector, and the question asks for the magnitude of the resultant force, and just like finding the magnitude of BA and BC, that's as simple as just adding all the square roots and then taking the square, or excuse me, adding all the squares of the components and then taking the square root of that. So going to step 6, magnitude of the resultant force is the square root of 90 squared plus 40 squared plus negative 50 squared. You're going to end up with the square root of 12,200 pounds, and that's roughly 110.45 or 110 if you're going to round down to 3 sig figs. Well, 1.1 times 10 to the 2 pounds if you're going to round to 3 sig figs, but that's semantics. So now that we have our FR, all that's left to find is the coordinate direction angles, and in order to do that, your cosine of whatever angle you're trying to find, whether it be alpha, beta, or gamma, is just going to be equal to that particular component of your force over the total magnitude. So if we're going to go to find, alpha, cosine of alpha is equal to your x component of your force over the magnitude. Take the inverse cosine, you get 35.4 degrees. Once again, I just did cosine -1 of 90, which is our x component, over the magnitude, which is the square root of 12,200. You just do the exact same thing for beta and gamma, except for beta you use the y component, which is 40, and gamma you use the z component, which is -50, and you should end up with 68.8 degrees for beta and 117 degrees for gamma. Alright, so we have our coordinate direction angles, we have our magnitude of our resultant force, so, well, this problem's done.